guys, a few days ago I posted a video with me setting up my paramotor for powered paragliding, and I made a statement about aviation engines not being very efficient, and that triggered a train of thought, and I thought I'll talk about what does efficiency mean and how it correlates to power. And by no means I'm an aviation expert or even engineering expert, but I do have engineering background, so I'll throw some theory in there. The aviation engines, they are not efficient as in the amount of mechanical energy output as the ratio of the heat or the thermal energy input is not as good as, say, a normal piston engine, right? Internal combustion engine. If you're talking about a jet engine, jet engines are extremely inefficient when it comes to converting the energy from thermal to mechanical. But because they are so light, the goal for an aviation engine to be able to take an aircraft from point A to point B, and at the heights that the jet engines fly, the distance they cover for a given amount of fuel is enormous. And if you wanted to put a traditional piston engine that has the same amount of thrust for that plane, it will be enormous, it will be huge, and the plane will never be able to take off. So although the conversion rate is low, the task that they need to achieve is actually achieved much more efficiently. And at a lower altitude where the air density is high, the prop engines actually perform better than jet engines. Jet engines are only effectively efficient and fast above a certain air density. So a turboprop, for example, if you have a turboprop or a turbofan plane, that's much more efficient at, say, a lower altitude like 20,000 or 15,000 feet. It's still not a piston engine. It has a turbine which is spinning a propeller, but it's the propeller that's giving you thrust, and you can calibrate and calculate a very effective range of the propulsion you need at different RPMs. So a turboprop fan is more efficient than a piston engine. A jet engine is even more efficient as long as it gets to fly higher. But if you're driving a car, for example this one, an internal combustion engine is much more efficient, because although it is a little bulky, you are driving on wheels, so an extra little bit of weight doesn't really matter. But the other thing that comes to mind is, in addition to efficiency, we also think about power. And power and efficiency are in complete opposite directions. If you want to get a lot of power out of an engine, say a 2-stroke engine, right, or even within 4-stroke engines, if you look at the Carnot cycle, it looks like a crooked parallelogram, and at every point it's a pressure volume graph, I believe. But at every point when you change the direction, what you are doing is you are making a change to the engine's stroke, right? So you input fuel, that's one stroke. You compress it, not stroke, but you compress it, that's one stroke. Then you ignite it, and that's what causes the expansion, that's your second stroke. And at some point you decide, okay, I have used enough energy out of this explosion of gas, so you open the valves and you let the gases go out the exhaust. At that point there is still a lot of energy left in that gas, but your engine is not suitable for taking that energy out. So even though you are burning a gallon of fuel, some of it is going out of the exhaust really hot and with unresisted expansion. In thermodynamics, unresisted expansion is when a gas expands but there is no piston to hold it and use that energy, so it just goes boom, right? And when there are no external factors, when you're not taking the energy out of the gas, it goes through something called an adiabatic expansion, where since it was compressed and the molecules have space to roam around and they don't have to vibrate as fast, the temperature drops, so it cools. It's adiabatic expansion and adiabatic cooling. But that's your loss of energy. How do you know which engine is lossy versus which engine is not? Whenever an unresisted expansion happens, it results in a loud sound, bang. And for example, I'm driving this car, it seems pretty quiet. It's because the exhaust is going through a series of muffling mechanisms. There's a muffler exhaust system. If you have ever seen a car where the exhaust falls off, it sounds like crazy. It's terribly noisy, and every stroke that is coming out without the energy of it being harnessed is unresisted expansion, and every stroke is making that noise. If you wanted to use more of that energy, you will have to make that engine a little larger so you can use that expansion for a longer period. But it will also mean that every stroke will give you less energy per quantity of time. So every second, every minute, if you are spinning at say 2000 rpm, every stroke gives you some energy. But if you make your engine larger and try to extract every bit of energy, your RPM will go significantly lower. So you might, instead of 2000 RPM, right now I'm driving at about 2000 RPM, the engine will run at much less, 1000 or 500 RPM. The energy per stroke is going to be slightly higher now because you are using that energy, but it's not linear. You won't gain the same amount of energy as you are losing in the RPM, because the tail end of that energy is much lower. The peak of the energy has already been extracted. The gas has a little bit more energy left, but it's not a lot. It's slowly expanding at that point. So engineers make a decision that at a certain point I'm going to cut off the cycle, let the gas exhaust, and put a fresh mixture of fuel, and then start the cycle all over again. So if you wanted to make a more powerful engine, what you will need to do is cut that cycle even shorter, and think of the power cycle as power gradient as something like this. As soon as the fuel burns, there's a lot of power, and as the gas expands, the power that remains in that cylinder goes down. So you want to be at the peak of the power, and you want to exhaust gases more often. That's what happens when you press the gas pedal really hard. Your engine spins faster, and in every stroke, before it can use all the energy, you are saying, I'm done, let the gases go out the exhaust and put some new fuel in so I can get more power. So power and efficiency are always going to be on the opposite spectrum of the measurement. So that's how it works, right? When engineers design an engine, they make those decisions, and based on that, you can get energy out of your engine, but it can be efficient or it can be powerful, but most likely not both. The other example of unresisted expansion that comes to mind is explosions, right? In military, when you have explosions, it's not a controlled explosion. If you wanted to utilize all the power of an explosive, you will need a lot of time and space to contain and use that, but we don't have time, right? When you are making an explosion, firing a bomb, The goal of the military is to achieve as much destruction as possible, life or property or whatever it is, right? You are trying to blow up a tank, you are trying to blow up a ship, you want that explosion to be as quick as possible. So efficiency is the last thing you have in mind, and that's why military explosions are so loud. If you look at the mining industry or demolition industry, you have all the time to plan your explosion, right? In a well-controlled, well-executed mining operation, when you blow up a mountain to make way for machines or to drill out your minerals, the explosions are almost invisible. Somebody presses a trigger and suddenly a bunch of rocks fall down, because what they do is they drill inside the mountain and put the explosives in very strategic places. So when the explosive goes off, all that energy is used to disintegrate the rocks, and the rocks just fall down. So in a good, well executed mining operation, when someone triggers a button, you won't even see the explosion. It will be just goes boop and everything falls down. Sometimes you do see those explosions. They are generally accidental. The explosion finds a way that was probably not planned for it, but normally the mining explosions are not very visible. Same with demolition. If you see a bridge being demolished or a building being demolished, they try their best to use that explosion. Sometimes you do see some explosive gas coming out. Even sometimes you see the sparks, but the best way to do that is to drill it in such a strategic place that the minimum explosive is used. If you see explosives flying everywhere in a demolition, think of that as wasted explosive. The same task could have been done with less amount of explosives. Same thing with the gun. When you look at a gun, and I'll show you a handgun. A handgun generally has about 3 inches of barrel, 3.5 inches of barrel. Some of it is occupied by the bullet in the chamber. The barrel includes some part of the bullet. Anyway, what happens is when the explosive fires, the bullet has about 3 inches to accelerate, and it goes from 0 to almost 1500 meters per second in a very short time. That's why you get that recoil. But as soon as it exits, there is still a lot of strength, a lot of energy left in the explosive, and that's what you hear as a bang. So as soon as the bullet exits, the gas that was trapped in the barrel expands really loud, and that's the sound you hear. That's why the gun, firing a gun is so loud. That unresisted expansion is what you're hearing at that point. If you take a rifle, rifles have much longer barrels. You get about foot and a half. Sniper rifles are even longer. That gives a lot of time for the bullet to travel through the barrel. Technically, with the same amount of explosive, if you look at the cartridge for a rifle versus a handgun, it's not very different. You still need, in fact, for a shorter barrel, you need more power, but with the rifle, what you really get is the longer travel for the bullet, and it acquires all that kinetic energy. By the time it comes out, one, it's moving really fast, and two, it's also spinning because you got this barreling inside the barrel, right? Spinning. But it gives a little more time for the bullet to acquire energy, and that's how they are more accurate, and they have much longer range. But with the handgun, again, your objective is not maximum efficiency. Your objective is making a shot as quickly and effectively as possible, and also concealing it in your pocket. If you have a longer barrel, you can't conceal it in your pocket, so the whole objective is lost. So that's how it is. There is always a compromise between efficiency and power, and as an engineer, one needs to make those decisions before while designing things like that. Where do you draw the line, and at what point you say, okay, I'm done with this cycle, let's move on to the next one. So all right, fun stuff.